Welcome back to this next video in which we are discussing the alternating groups. Okay, so we've now seen that this sine function is indeed a group homomorphism from the symmetric group on the set of n elements into this group that is isomorphic to the cyclic group on the set of 2 elements containing +1 and -1. What I want to do now is show you that all transpositions in the symmetric group on the set of n elements have sign -1, they are odd permutations, and then what we will finally do is understand how this does capture the initial concept that we wanted it to capture in terms of decompositions into transpositions. Okay, so firstly then, to show you that all transpositions are odd permutations, and in fact I think I will write that as this little theorem. I might call this a little theorem here. All transpositions are odd is what we want to show. In order to do this, what I'm going to firstly show is that just one transposition in particular is odd, and then we'll use that to show that all transpositions are odd. Okay, so all transpositions are odd. Okay, so I'm going to pick a very special, very easy transposition initially to prove that is odd, and then we'll use it to prove that all other transpositions are odd. So the first one that I'm going to use is the transposition which swaps 1 and 2. So remember, we are thinking always of working with symmetric groups that are on the set of 2 elements or above. I am not interested in the symmetric group on the set of 1 elements. That is the trivial group. Okay, I'm not interested in that one. I'm interested in S2 upwards. So this will always be a transposition that exists in S2 upwards. And the claim is that I can very easily show that this is odd. Now, the best way for me to do this is just to proceed with an example. That's the best way to get intuition for this. If I try and explain it in general, it will just become more complicated than it needs to be. So I'm just going to do an example. I'm going to do the example once again with n is equal to 4. So I'll just copy my polynomial delta 4 out again. So remember, this is x1 minus x2 times x1 minus x3 times x1 minus x4 times, I hope I'm going to be able to fit it in, x2 minus x3 times x2 minus x4, it looks like it, times x3 minus x4. Okay, so here's my polynomial, delta 4 here. Okay, now let's think about acting this transposition on this polynomial. Now what's going to happen? Well, this one here, we're going to send 1 to 2 and 2 to 1, so that one's going to flip, and I'm sorry, I've just drawn on that one, x2 minus x1, so that one does flip. When we do this one, we'll get x1 going to x2 and x3 will remain constant. When we do this one, x1 will go to x2 and x4 will of course remain constant. When we do this one, x2 will become x1, so we'll get x1 minus x3. Again here, x2 will become x1, so we'll get x1 minus x4, and here neither 3 or 4 will change, so we'll just get x3 minus x4. Okay, so you can see that the only one here that has flipped is this initial one here, which is exactly why I've chosen this. Okay, because that is the only one that will ever flip in general. Okay, and let me emphasize the reason that that's the only one that has flipped here. Look at all the ones where x1 appears. The only terms, of course, that we're interested in are those that contain x1 and x2. So look at all the ones that contain x1. x1 always appears in the first position because 1 is lower than any of the other numbers that we're going to be using. So x1 will always appear in the first position, and you're just going to be changing that to x2. Now the only one that's going to flip from you doing that is the one where you've actually got x2 here, so you've got x1 minus x2. All the other ones, so x1 minus x3, x1 minus x4, more generally it will go on to x1 minus xn. All of those are not going to flip because all you'll do is change x1 here to x2, and that doesn't make any difference at all because x2 is still smaller than all the rest of these. Okay, so those aren't going to flip. The only one that's going to flip is x1 minus x2. Now let's think about all the ones that contain x2. Well, the only terms that contain x2 are this one right at the front, x1 minus x2 here, and then the ones where x2 is in position 1. So this is the only case where x2 will be in position 2, because x 1 is the only one that beats it basically to position 1. All the other numbers won't beat 2, and they'll be in the right position and 2 will be in the left position. So we've got x2 minus x3, x2 minus x4, etc. all the way up to x2 minus xn in the general delta n. Okay, and when you change this to x1, those are not going to flip, because you've actually made it better. You've gone from using 2, second place, to going to 1. 1's stronger. 1, if 2 beats these ones to the left position, 1 is certainly still going to beat them. Okay, so when you replace this with x1, of course, it doesn't change the order, it doesn't flip it. These are still in the correct order. Okay, so those are not going to flip. So in fact, I hope that I've now argued that this truly is going to be the only one that flips, not just for delta 4, but for delta n. Okay, so in an arbitrary Sn, so this in Sn is odd. Okay, whoops, not like that, is odd. Okay, it has a single flip. It only flips that x1 minus x2 term and doesn't flip any of the others. And I hope my argument there has convinced you that that will be true in the arbitrary Sn with this arbitrary delta n. Okay, so bingo! I've concluded that one transposition in the symmetric group on the set of n elements is always going to be odd. How can I use this now to prove that all general transpositions in the arbitrary symmetric group on the set of n elements are going to have odd signs, are going to have the sign -1? Okay, well, let me take an arbitrary transposition now, the transposition which flips I and j, where I and j are just natural numbers. Okay, and we're now working in Sn. Okay, so there's a beautiful trick here. You can turn this, well, you can use the transposition of 1 and 2 to describe this. And let me show you how. Okay, a picture is the best way to do this. So if I draw this out, 1, 2, and let's have I here, let's have j here, so I'm just drawing my set 1 to n here, and look, I've got I and j here, and I need 1 and 2 also here. Okay, now I'll just copy it out again. So I, j, all the way up to n. So the way I'm going to turn this transposition, or rather use the transposition of 1 and 2 to understand the transposition of I and j, is I'm firstly going to swap 1 and I around. Basically what I'm going to do is I'm going to decompose this transposition into something, then in the middle the transposition of 1 and 2, and then the thing back again. Okay, and I'm sorry, that isn't a brilliant explanation, but you'll see when I draw this out. So the best way to proceed, I think, is me just drawing this out. So I'm going to swap 1 and I around, and I'm going to swap 2 and j around. Okay, and then I'm going to fix everything else. So in particular, n will get fixed here. Okay, so let me colour these in. So here's one of these. I'm swapping 1 and I around. Okay, and remember, I'm trying to create the transposition of I and j here. Okay, using the transposition of 1 or 2. So this looks like something vaguely sensible to do. Send I to 1, j to 2, and then transpose 1 and 2, and then just fix it back again. Okay, return it to the way it was, so that overall you get the transposition of I and j. Okay, so those are the only things we'll be moving. This element, which I'll call alpha here, is going to be a permutation in Sn here. Okay, and what's it going to be? It's going to be 1, swap 1 and I around, so that 2 cycle, and also swap 2 and j around. This is its cycle decomposition, and everything else is fixed, so everything else is in a 1 cycle, and therefore you don't bother showing them. Okay, so here is this element here. Okay, now what I'm going to do, of course, is just swap 1 and 2 around, perform the transposition of 1 or 2. So I'll draw my entire set out again, I'll transpose 1 and 2, and of course I'll fix everything else, so I, j, and n, and everything else will get fixed. So this is now just the transposition of 1 and 2 here, okay, in the middle. And now let's just undo what I did at the start, and let's hope that that actually works. Okay, and hopefully you'll realise that it is going to work. Okay, so here is the set again, and now what I'm going to do is I'm going to do the exact same thing I did before, alpha, but now I'm going to undo it, because of course it's its own inverse, so it's now going to invert itself like so, and of course it fixes everything else. So I'll just colour that in again. So here is the transposition of 1 and I, this portion, and in green this is the transposition of 2 and j here. Okay, and hopefully that now works. Hopefully this structure that I've created here, this is a decomposition of the transposition of I and j here. Okay, so let's just work this out. So where does 1 overall go to? Well, 1 goes to I, goes back to 1. Excellent. 2 goes to j, goes back to 2. Excellent. So that's very good. 1 and 2 are fixed. That's exactly the way we wanted it to. Everything else apart from I and j is totally uninvolved in this, so we won't even bother looking at those. They're just fixed by everything. Now let's look at I. I goes to 1, goes to 2, goes to j. It's looking good. Where does j go to? J goes to 2, goes to 1, goes to I. Excellent. So what I've managed to do here is decompose the transposition of I and j into alpha composed with the transposition of 1 and 2, and then composed with alpha again. So I can write this like so. Firstly you perform alpha, then you perform the transposition of 1 and 2, and then you perform alpha again. Okay, so any transposition can be decomposed like so into this thing alpha, which of course will depend on what I and j is, and then the transposition of 1 and 2. Now why does this help me in concluding that the sign of the transposition of I and j is equal to -1? Well, let's just do it. Okay, the sign of the transposition of I and j is of course going to be equal to the sign of this, but we can now use the fact that the sign is the group homomorphism to split this into the sign of alpha times, oops, missed out the sign of the transposition of 1 and 2 times the sign of alpha again. Okay, now of course we know that the group plus or minus 1 is an abelian group. This is an abelian group, so we can move things around as we please. So this will become -1 for this, -1 times the sign of alpha squared. Now why is that brilliant? Well, because no matter what the answer to this is, no matter what the sign of alpha actually is, whenever you square it, it'll just become +1. -1 times -1 is +1. +1 times +1 is +1. So the sign of alpha squared is just going to be +1. So this is truly just going to become -1. And that's the genius of this. Okay, so we can use the fact that the sign is a group homomorphism to prove that the sign of any transposition is going to be odd, i.e. -1. Excellent. So we now know truly that all transpositions in the symmetric group on the set of n elements are going to be odd. They're going to have sign -1. Okay, right. Now, finally, we piece this all together and understand why this captures the concept that we started off trying to build. This concept that any set permutation in the symmetric group on the set of n elements, if you decompose it into a series of transpositions, is either going to have an even number of transpositions or an odd number of transpositions. Okay, so this is how we can do it then. So if I've got some sigma in the symmetric group on the set of n elements, and again I'll remind you that we're assuming n is greater than or equal to 2, okay, let's say I have decomposed it into a series of transpositions. So let's say that sigma can be written as, let's say, tau 1 composed with tau 2, composed with tau 3, etc., all the way down to some tau m. The claim is that no matter which decomposition into transpositions you come up with, the parity of that always remains the same, i.e. whether you've got an odd number or an even number remains the same for this specific element. Okay, yes, for different elements of the symmetric group on the set of n elements it might differ. There will be some that have odd numbers and some that have even numbers, but for a specific element, any decomposition that you have into transpositions will always contain either an even number or an odd number, okay, no matter which of the decompositions you come up with. Okay, right, so how can we prove this? Well, of course, now what we can just use is our group homomorphism, the sign of this. We can say the sign of sigma is going to equal the sign of tau 1 times tau 2 times tau 3 all the way along to times tau m. This has some answer. It is either +1 or -1. It's a fixed answer though. Okay, it has a fixed answer. Now, On the other side, we can apply the fact that this is a group homomorphism to say that it's just the sine of tau 1 times the sine of tau 2 times the sine of tau 3 all the way up to the sine of tau m. But of course, each of these is just a transposition. Okay, so its sign is going to be negative 1, so this is just going to end up being negative 1 to the power of m, i.e. negative 1 to how many, to the power of how many transpositions you've got in this decomposition into transpositions. Okay, so if the sign of this permutation is plus 1, this had better be an even number. And if the sign is negative 1, this had better be an odd number. Okay, so if the sign of a set permutation is plus 1, then any decomposition into transpositions that you can possibly build of it must have an even number of transpositions in it. And if the sign of a set permutation is negative 1, then any decomposition you can build into transpositions for that element better have an odd number of transpositions in it. Okay, so there's the final answer as to what this sine function has to do with the parity of the number of transpositions in any transposition decomposition of a set permutation. Okay, so there is finally that bit put to rest. Okay, so we know that this sine function truly does do what we set out to do. Okay, it ascribes plus 1 to set permutations, which if you decompose them into a series of transpositions, will always have an even number of transpositions there, and it ascribes negative 1 to those set permutations, which if you decompose them into transpositions, will always have an odd number of transpositions there. Okay, what I now want to do is firstly talk about the fact firstly what I want to talk about, what I want to talk about now is the fact that this sine function, epsilon, is actually going to be a surjective homomorphism, and about how we can actually now construct the alternating group on the set of n elements. That's where I want to go now. I want to construct the alternating group on the set of n elements. So firstly, just allow me to say that this is going to be a surjective homomorphism. So the sine function on the symmetric group on the set of n elements, which will ascribe to all of the elements of this group plus 1 or negative 1, is going to be a surjective group homomorphism. And why is that going to be true? We know that it's a group homomorphism. Why is it always going to be the case that it's surjective? Well, surjective means that it's onto. So all I need to prove is that some elements will be carried on to plus 1 and some elements will be carried on to negative 1. Well, the identity element here is always going to go on to plus 1. Okay, because if you think about it, the identity element just fixes all of the elements of the set 1, 2, 3, all the way up to n, so it won't change that polynomial delta n at all, okay, and therefore it will have sine plus 1. In addition, provided that we know that n is greater than or equal to 2, we know that the symmetric group on the set of n elements will always have at least one transposition in it, okay, and we know that that transposition will have sine negative 1. So both of these get hit, basically. So we can conclude that it's a surjective group homomorphism. Okay, so now what we can do is we can consider what's the kernel of this group homomorphism. Okay, what is the kernel of the sine function? Okay, and we know that that's going to be a normal subgroup of the symmetric group on the set of n elements, and that is what we're now going to call the alternating group. Okay, so it's going to be a normal subgroup of the symmetric group on the set of n elements. Now, which set permutations are going to be in the kernel of the sine function? Okay, well, it's going to be all those set permutations that are mapped onto the identity over here, which of course is plus 1. It's going to be all those set permutations that are even. So that is the definition of the alternating group on the set of n elements. It's the set of all set permutations of the set of n elements that are even set permutations. Okay, so we've now defined that. Now, by the first isomorphism theorem then, if you were to quotient out the symmetric group on the set of n elements by the alternating group on the set of n elements, you would end up with something isomorphic to the image of this group homomorphism, okay, which we know, because it's a surjective group homomorphism, is going to be the entire group over here. Okay, that tells us what the index of the alternating group on the set of n elements in the symmetric group on the set of n elements is going to be. It tells us that it must be 2. Okay, so to draw a picture of this, that's that the entire box here be the symmetric group on the set of n elements, okay, then this subgroup here, this subportion, this is the alternating group on the set of n elements, and it will contain exactly half of these elements in the symmetric group on the set of n elements, okay, because as I say, if you were to quotient this, the symmetric group on the set of n elements out by the alternating group on the set of n elements, okay, you would end up with a group isomorphic to this. Okay, this coset would become the equivalent of this one, and this coset would become the equivalent of this one. Okay, so indeed, this will equal all the elements that have a positive sign, okay, all the even permutations, and this coset of it, this left or right coset, doesn't matter because it's a normal subgroup of the alternating group on the set of n elements, would then be all of those permutations with -1 as their sign, i.e. all of the odd permutations. Okay, so that allows us to say what the order of the alternating group on the set of n elements is going to be. It's going to be the order of the symmetric group on the set of n elements, which is n factorial divided by 2. Okay, right. And that's all we're going to say about the alternating group on the set of n elements in this video. It's just a basic introduction to this group. The final thing that I want to just point out is how do you actually work out whether a given set permutation is odd or even, okay? So we started the video by seeing that all set permutations in the symmetric group on the set of n elements could be decomposed into a cycle decomposition. We then saw that any cycle permutation could be decomposed into n-1 transpositions. Okay, so if you want to work out whether a given set permutation, let's say sigma, in the symmetric group on the set of n elements is odd or even, you just need to take its cycle decomposition and look at the lengths of the cycles. You then need to say, okay, go along each of the cycles in the cycle decomposition, take one off from that length, okay, and then add all of those numbers together, and then if that's an even number, then it's going to be an even set permutation. If it's an odd number, then it will be an odd set permutation. Okay, so if I bring back up my original piece of paper here with this example from S8, so remember this element could be decomposed into this cycle decomposition here. So we've got a 5 cycle and a 3 cycle. This 5 cycle could be written as 5 minus 1, which is 4 transpositions by, where is the theorem? This theorem here. Okay, a cycle of length m can be broken down into m minus 1 transpositions. This 3 cycle here could be broken down into 3 minus 1, which is 2 transpositions. So add those two together and I get 6. So overall I could write this element as 6 transpositions, meaning that overall it must be an even set permutation, i.e. it would be in the alternating group on the set of 8 elements. Okay, so that's how you can actually work out whether a given set permutation is going to be even or odd. Okay, you just decompose it into its cycle decomposition, which we know, and then count the lengths of each of the cycles. Take one off the length of each of the cycles and add them all together. If that number is even, then you know that it's going to be an even set permutation. If that number is odd, then you know that it's going to be an odd set permutation. So hopefully that will help you out if you ever actually want to construct the alternating group on the set of a certain n elements. Okay, now stress finally, just to end with, you must do this with n is greater than or equal to 2. Don't try and do it for n is equal to 1. It's just not relevant when n is equal to 1.